Okay, so we move now to the second talk. We change a little bit field. It is my pleasure to actually introduce a former ESO fellow, Annalisa De Cia, she's now at the University of Geneva, and she will tell us about UVES and transients science.
Ciao Francesca.
Ciao Annalisa.
Ciao to the many familiar faces. Let me share the screen. And while I do this,
I will give you a few minutes warning, right?
Yes.
Okay.
Yeah, be loud, thanks. Do
Yeah.
you see my screen?
Yes, very well. Thank you.
Great. So thanks for inviting me here to talk about transients today. And thanks for also all the people that have been working on UVES and science. Most of it has actually happened when I was still a baby in this field. So yeah, let's talk about transients today. Transients immediately tells you it's a zoo. So we have very many different transients. It's like a vast and diverse field with many different objects. And I won't be complete for sure. Like this is too vast. Mostly I will focus, I will give some highlights from supernova science, gamma ray bursts, a bit of novae. And even in one subfield, like narrowing it down to a few of these class, like supernovae or novae or so, or TDEs, there's still a variety inside this class of transients. So it's really a zoo in the zoo. Why studying transients, first of all? Well, they give an incredible opportunity. Something all of a sudden goes boom, lightens up something in the dark. So it's an opportunity to study in depth that particular object that would not be possible otherwise. So we get new insights. Sometimes we get new physics. And of course, then we are open to the unexpected. There is a but, or many. So first, we don't know where they go off. So that's a level of difficulty. But they can also be very rare. They can be very faint, and they can be very quick. So it adds to the difficulty of discovering and following up these objects. And when it comes to UVES, this means that we will be restricted or limited to the few objects that are bright enough to be observed with UVES. So you won't give the numbers, like the large statistics, but mostly like deep insights into a few very interesting objects. So first highlight, supernova 87A, core collapse supernova, type 2 supernova that happens around the corner, so in the Large Magellanic Cloud. We saw this image from UVES first light yesterday already from John. Thanks for pointing it out. Because it was so bright and so far away, really it gave the opportunity to go into the physics of this explosion and see incredible details. What is shown here most bright is the ring. So the interaction between the supernova ejecta and this ring of material that had been ejected long before the supernova went off. And specifically, UVES gave fantastic results on this. So, for example, it showed how the emission lines coming from this ring were varying in time. Following the evolution from the first light, 1999, to 2007. And as you can see in these panels, like the emission lines have been varying during these years. And this is because these lines had been excited before ionized and excited before by the shock breakout of the supernova. And then later, the flux of these lines have been slowly going down. with the exception of some lines, like the more ionized, like oxygen-3 and neon-3, who increased. And not only the intensity of this line have changed, but also the kinematics of these lines. And this gave incredible details for scientists then to go into modeling these observations and really working out the physics of this incredible object. Another supernova. This is a supernova 1A, a normal supernova 1A. And of course, one of the big issues that we have in astrophysics and cosmology nowadays is what are the progenitors of supernova 1As, because we use them for cosmology, but we don't know exactly how they are produced. So in one case, Nando and colleagues, they could observe incredible, very strong variability of the sodium-1 line with UVES. And this was the first spectroscopic evidence for circumstellar material that had been detected before, because only the sodium-1 line was varying, not the calcium-2. So it was really material that was changing due to the circumstellar material that was being ionized and was reacting to the supernova. On the other hand, there were other works where no circumstellar material was detected, and it was excluded for the case of Mattila et al. 2005, also with UVES data. More on supernova progenitors. There is another object on supernova 2N, so with showing interaction with their circumstellar material. In that case, using again UVES data, there was scientists proved that there was a link between the supernova and the progenitor. In this case, the progenitor was probably a luminous blue variable because of the similarity in the H-alpha profile between the spectrum of the supernova and LBVs. And then something that is related to progenitors, not direct, well, it's related to progenitors of supernova 1A. So this was a large program with UVES, observing white dwarfs and trying to count how many of these white dwarfs have companions. And so the double degenerate fraction was found to be of 6%, so not that high. On to novae as sources of beryllium and then lithium. So recently, this is from Paolo, 2020, well, they observed the brightest novae they could. So the 4 very bright, I think it was the brightest in the past couple of years or so, with UVES to search for beryllium-7. And what I wanted to highlight is that for this kind of search, they had to look for doublets that are at 300 or so, 330 nanometers, meaning in a place where the atmospheric absorption is very high, and also the efficiency of the spectrograph is low. So this would be also important to keep in mind for our discussion in the prospect of an eventual upgrade. So they observed the 4 novae. They detected two they detected, 2 they didn't detect. So not all of them eject beryllium. But what was important was that the abundances that they found were very high. So the abundances that they found in beryllium decays in lithium. So it would mean an overproduction of lithium by a factor of 4. And this could be likely a missing source of lithium, which is missing in the galaxy. So now I go on to gamma ray bursts. So gamma ray bursts, well, they are associated with with the death of massive stars. And one of the facts why we know this is because of this one object here. This is a GRB, and what you see in the figure is a spectral series that evolves into from a GRB, and the afterglow eventually evolves in a supernova. And I put this one here because UVES was the one actually to find the redshift for this source. It was a very, very, very nearby one, 0.17. That's very low for a GRB. Because in fact, most GRBs, they're rare events and they explode far away in the universe. So here is a redshift distribution of gamma ray burst, more or less updated to this year. And as you can see, we can see gamma ray burst out at very, very high redshift. And we can use these as cosmic beacons. Suddenly bright star-forming galaxies, and we can study these star-forming galaxies and the whole line of sight for maybe a few hours, a day or so, and then they're gone. And on the right side, I report the sample that we have at the moment with UVES. It's 17 GRBs, so it's the brightest tip of the iceberg. Importantly, with gamma ray burst, we select star-forming galaxies that are small and distant, and they're virtually invisible sometimes. They're too faint to be studied with other media, with other techniques. And when we do absorption-line spectroscopy, well, we heard a lot about this earlier. We can learn a lot about the interstellar medium and the circumgalactic medium. And we can learn the properties of this gas in these star-forming galaxies or along the line of sight. We can learn about the quantity of the gas, the gas content, the metal content in terms of metallicities, abundances, the content of the dust, molecular content, like we heard also earlier from Pascal, and the kinematics. And here I report one example from a paper from Cedric, where they showed the column density of hydrogen versus the proxy for the metallicity this is for quasar DLA. So the blue and the black ones are for quasar DLAs. The black ones are where molecules are detected, and these 5 ones are from UVES without molecular detection. That's from his sample there. One other thing that we can do with GRBs is studying the cosmic chemical evolution. So out to high redshift, we can ask ourselves, what is the metallicity of the neutral gas? And we did this first with quasar DLAs, and here with metallicity, I mean dust-corrected metallicity. And I would like to stress here that UVES was absolutely fundamental to figure out the dust corrections that go into this for the quasar DLAs, but this is for another talk. What about GRBs? So here, these are GRBs until before 2009. So here you see highlighted the ones from UVES. And you see that there are many compared to, well, there's several of these were observed with UVES. Note, however, that there are many UVES GRB afterglows that are missing from this picture because either a couple of them have a lower column of neutral hydrogen, so they don't appear in here, or because they have to be bright, they're actually below, in the redshift range where we don't observe the hydrogen, so we cannot calculate the metallicity. So there are more GRB from UVES there. After 2009, Edge Shooter came, and then it started to populate this this picture more. So UVES here is not giving the great numbers, But where UVES really gave its best was with the rapid response mode. And here I'll make some fun. This is what happens with at the control room. In UT2, every now and then, the rapid response mode goes off. Not too often, but yeah. So, whoops, we want to stop this. Okay. Okay, obviously let's start from here. Yeah, so the rapid response mode was put up at commissioned at VLT in 2004, initially for UVES. Nowadays it's on many more instruments. It allows immediate GRB follow-up. This is important because GRBs fade quickly. So with this, you can be on source within 5-10 minutes already integrating on the source. And this allows the community, to observe variability of the absorption lines. So here is an example here where you see two lines. Well, it's apparent column density. So at two different epochs, blue epoch 1, black epoch 2, they vary dramatically. And these are lines that are, is this 5 minutes or?
Yes, it's 5 minutes to go.
Okay. So what you see here is that excited lines of iron 2 are changing and reacting to the GRB flux. And also resonance lines, like ground state line of iron 2 is varying because it's being ionized to iron 3. So you see ongoing photo excitation and ongoing photo ionization in this galaxy that is maybe at redshift of 2.4. So this is so from the absorption line variability, people like Paul Vreeswijk or Valerio Delia have been very busy modeling this the fluxes of the variability of these lines, and probing that it is the effect, the ongoing effect of the GRB that produces the variability of these lines. And not only through photoexcitation, but also through photoionization. And through this modeling, they could tell the distance from the GRB. So the distance between the gas that is absorbing, the ISM, the bulk of the gas that is absorbing, and the GRB. So not only we can tell what is the metallicity, the relative abundances, the kinematics, the molecules in this very far away galaxy, but also we can tell the actual geometry in a way, like the distance between the GRBs and the absorbing gas. In a way, it's a proxy for the size also, or it gives an indication on the size of the galaxy. And again, these are galaxies that otherwise would be barely detected in flux, if any. This is a table with GRBs that have been observed where GRB distances from the gas were determined through the observation of gas absorption line variability. And as you can see, many of them has been determined thanks to UVES, which has really been unique, and thanks to the rapid response mode with UVES. After a certain period, then X-shooter started to come in. So you see, after it was commissioned, so from 2009 on, mostly there were X-shooter bursts with absorption line variability and with distances estimates. So another highlight, something I worked on was GRB O8310. It was Redshift 2.4. Here you can see just an example of a few of the absorption lines, and it really gave some light to some exotic environment, both in terms of chemistry and physics. So it had a very low neutral hydrogen. It had a supersolar abundance of iron and chromium. We saw ongoing photoexcitation and photoionization. Then from the modeling of the absorption line, it came out that there had to be a foreground cloud that was completely ionized, very nearby the GRB. And then the distance of the gas that was mostly absorbing was like 200 to 400 parsec from the GRB. Now, in this burst, we discovered some levels of iron-3, like some iron-3 excited lines that were never seen before in these types of environment, like neither GRB absorbers, quasar absorbers. Because we saw them, so we saw that basically iron-2 was being ionized into iron-3. But a large fraction of the iron-2 that was going into iron-3 was actually falling not on the ground state, but to an excited level, like the 17th excited level of iron-3. And then it was decaying. This excited population was decaying down to the ground state. And by just observing these lines and this variability, we could give new, actually predict the atomic transitions, the new probabilities that for this level. This is 2 minutes. Right? Good.
Time is up officially.
Oh, okay. Right. Then I will drop this and go to the essential features for transient science.
You can conclude, yes, of course.
Yes. So, well, just 2 slides because they are important for this discussion. So what is essential that we currently have in UVES for the transient science? High sensitivity, number 1, then well, I don't know how to prioritize them now, but high sensitivity and resolution, the wide wavelength coverage, because we have sometimes unknown Z, the blue coverage of the spectrum, and having a slit, because the spatial information is sometimes important. Operationally, the rapid response mode capability has been fundamental for GRB science with UVES, and also the fact that some proposal, let's say flexibility, for example, including the rapid response mode in large programs, which is something very recent. Now, what we wish, or what is the wish for transient science, or what I could come up with some input of some colleagues as well. Well, the main limiting factor for us is that events that are bright enough are rare. So increasing the throughput is paramount, or well, it's among the highest priority if we think about an upgrade for us. And especially in the blue, for example, well, for GRB science, but also for supernova and novae. Especially for novae, for the beryllium search was fundamental. And operationally, well, we saw that UVES has suffered from the arrival of F shooter. So the policies of the main limiting factor is the fact that UVES has been linked to rapid response. And the pressure on UT not always allowed for this to happen. So I will conclude here.
Thank you very much, Annalisa. We have actually a few questions for you. So I will start with Riaz.
My question is about the slide which was mentioning the gas distances from the GRBs.
Mm-hmm.
So the question is that, is this the gas which is, I mean, the GRB nearby the gas is near the source, or it's the distance from the observer to the gas which is nearby the GRB? What's the case?
So there is gas around the GRB. You know, GRB is probably in a star formation environment, so it's a massive star, so there is gas, but this gas is probably completely fully ionized. The GRB is energetic, has a hard and intense radiation that fully ionizes that immediate environment, so out to maybe tens of parsecs. And then what we see here, it's the lines that are, the absorption lines are associated with the ISM. So this is the bulk, let's say the distance of the bulk of the ISM, distance between the GRB and the bulk of the ISM that we observe towards us.
Okay.
Did I answer your question?
Yeah, thanks.
Okay, next question, Celine, please.
Yeah. Hi, Annalisa. Thanks for a talk with a very broad overview of these main topics. I hear that you are emphasizing the role of a rapid response mode. And I see that, you know, every few decades, we are moving into a population of objects that are changing on smaller time scales, right? We went from supernovae month scales to GRBs days and FRBs. So probably there will be in the future a transient on, you know, we will manage to observe transient on even smaller time scale. So my question to you is the VLT, is UVES ready to observe those objects, do you think?
Well, I think at the moment, so that the record holder, like the quickest response we had was, I think, it was like 8 minutes, like 7 or 8 minutes after the GRB on source. And the limitation to narrow down, to lower down this time, is in the slewing of the telescope, because that takes like, depends on where it is, but you know, if you have to slew the telescope and then you have to do an acquisition. So, you know, for the record holder, the acquisition was done, I think Cedric was at the telescope, and he, you know, it just immediately went through with the RRM, immediately put the object on the slit, like very clear. And in this sense, the only way we could get it faster is by improving or make the slewing, the whole acquisition faster.
Right. Thanks.
Pointing the telescope.
Yeah.
And guiding.
Yeah, so I think that it makes sense, I mean, that we listen also to a couple of more questions, even if we lose a few minutes compared to the schedule. So I would call Elena Mazon.
Okay, I think I was after Lucas Bordone, but since I have the microphone, I ask. My question is about the resolution that is needed for this transient, mainly for the GRB science, because even in the slide that you are showing, it seems that you can interchange between UVES and X-shooter with no problem. And so I wonder whether there is a minimum resolution that you need or not.
Yeah, it's a good point. So it's I wouldn't say that we can interchange between X-shooter and UVES. Whenever we have a UVES spectrum, it gives much more information, and the measurements are much more reliable. So it's by far, so it's really a different level. Now you can do some things with X-shooter, like measuring the distances, for example, but and also determining the column densities of the different metals. But it's always on the maybe. So there's always a level of so first, the reliability of the measurement is on a different level for UVES, and second, the amount of information we get for a single UVES spectrum, it's unsurpassed by X-shooter.
Okay,
So
and you limit it to what type of magnitude? 20, 19?
Yeah, yes, even yes. I think it's borderline because the thing is when we observe, we don't know how bright it will be.
Mm-hmm.
So we cannot do we cannot do this game of what it's always a bit of a bet in a way, or well, we have some indications from the optical counterpart, like the first indication of the optical counterpart of the GRB, but then it decays very quickly. So maybe you start with a GRB that is 17th magnitude, but then in a couple of hours, then it goes down by 1 magnitude, and then 1 or 2 magnitudes, and then it's in the gray zone. What signal to noise then can you get with an hour or so?
Luca?
Yes, mine is mostly a comment. Actually, your operational wishes are satisfied now because the shooter was moved to UT3, has been recently recommissioned. And since I think period 105, but actually period 105 never happened, as we know, UT2 is capable to change focus when an RRM is triggered. Of course, it takes longer because it has to change focus. It takes about 15 minutes instead of 5. I don't know how it is the state of the commissioning on the other telescopes, but it's being commissioned the same thing also on the other telescopes. So shooter should be able to do it either already or very soon, depending on when the commissioning takes place. That was all I wanted to say.
Yeah, thanks. Okay. Go ahead.
Yeah, last question. So Amelia Bio.
Yeah, thanks. Well, it's more a comment for the discussion probably that RRM, the number of alerts that we are going to get is going to get ridiculously large, right? I mean, we know that. And I guess RRM will need to evolve also, and there will have to be some sort of sorting broker of alerts, and a lot of work is being done around the Vera Rubin Observatory. So I really think that is something that we have to start thinking about that already, how to efficiently handle all the alerts for all the transients that are to come.
Yeah, indeed, I put here a slide of, if we're talking about transients, then and the future, then to put it in the context of what's happening in transient science and the facilities that are coming up. So indeed, like some material for discussion, perhaps.
Okay, I think that we had a very nice set of questions. Thanks a lot, Annalisa, again.
Thank you.